Okay, so let's dive straight into the most simple form of the Heaviside step, which has the appearance of ut. So let's just have a look at this. So it's just going to, whenever you see a function f of t equals ut, what that means is very straightforward, very easy, something that you've probably come across before. So you have t, the x-axis, and f of t over here. F of t ut just means that before the x-axis is 0, it's going to be 0, and then after x equals 0 and onwards, it's going to be 1. So the actual function looks like this. And this goes on and on and on for infinity. So that's the Heaviside step function. Now, if we have, let's make it a little bit more complicated. If we have f of t equals u of t minus c, okay, all that is, you can probably guess, is the Heaviside step function with a positive shift. So remember, when we have a minus inside the argument, that moves it to the right. If we have a positive, that always moves it to the left. So if we have t minus c, then that's going to look like, again, we have the function over here, f of t, and t over here. It's going to look like over here, and then over here. And that's going to be 1. And this value over here is going to be c. See that over there? So that's all it is. It's as simple as that. The Heaviside step function, f of t equals u, t minus c. U, t minus c. So if we had the Heaviside step saying, so it was u, t minus 3, then that would be, this would be 0 until t equals 3, and then it would go to 1. And if we multiply this with any function, we can now effectively turn the function on and off. Well, on, at least we can turn it on for now, at any point in time we want by choosing the value of c. So if we have, let's say we have, let's do an example of, say, x squared, why not? So we know the function f of t equals t squared, yeah? Know what that looks like, I hope. So it's going to look something much better than this wonky thing, but anyway, you get the idea. And that's going to be t. Yeah, it's going to kind of go like that, t squared. Now let's say that we have another function, I'm going to do in a different color, of say f of t equals t squared times u t minus 2 dot u t minus 2. So what do you think that's going to look like? Well, we know what ut minus 2 looks like. Ut minus 2 is going to be this. It's going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, until we get to the value that t equals 2. And then it's going to turn on the value of 1. Okay? And above it, that should be 4. Right? The scale's terrible, but that should be 4. Because 2 squared is 4. So that's the Heaviside unit, the Heaviside step function. And we've got t squared. So if we multiply this by this, we're going to end up with, the function will be 0 for every value less than c, in this case 2. So it's going to look like 0, like all the way over here. And then it's going to jump on, it's going to turn on, because everything beyond 2 is going to be multiplied by 1. Well, that's just going to be the entire function, whatever it is up until that point. And then it's going to go to 0 immediately. So that's, in the red line, is what this function, or the product of those two functions, are going to look like. They're going to look like that. Let's have a look at another one. What happens if we have f of t equals sine t? Well, we know that sine t is going to look something like that. That's 2 pi t and f of t. And that's going to be 0. And let's have another function. Let's call it g of t equals sine t times u t minus pi on 4. So what do we think that's going to look like? Well, we know that this is pi on 2, and that's going to be pi on 4, just over here, isn't it? And we know that ut pi minus 4 is just going to be 0 for everything left of this line. And then it's going to be 1 for everything beyond that line, to infinity. So that will have the effect of turning the function off for every value previous to t equals pi on 4, and turn the function on for every value in front of pi on 4. So the combination of g, t, sine t, ut minus pi on 4 is simply going to be that, and then the rest of the function. It's a little bit difficult to see that, but that's effectively what the function is going to be. 0, 0, 0, all the way to pi on 4, and then it's going to turn on. Okay, now let's consider what happens when the argument of the original function is exactly the same as the argument of the Heaviside step function. So let's say we have sine t minus pi on 4. We multiply that by ut minus pi on 4. What does that look like? Well, let's have a look. So we know f of t. We know that sine t is going to look something like this. So sine, if we have, let's do that over here, if we have f of t equals sine t minus pi on 4, that's going to be shifted to the right by pi on 4 units. Yeah. So this is going to be over here. This is going to be, I think, over here. That's going to be over here, and that's going to be over here. Is that right? No, it's going to be over here. So I think it's going to look something like, well, something like that. Everything, the whole sine wave is shifted pi on 4 units that way. So now we have sine t minus pi on 4, but remember, we've got that as well, between 0 and 2 pi. Now, if we multiply sine t minus pi on 4 by u of t minus pi on 4, what do you think we're going to get? We're going to end up with just this part over here. Just that bit. You can see that a little bit thicker. Why? Because this part over here is going to have the value of 0. And we can actually represent that by extending the function like that. So it's going to be 0 for every value before t equals pi on 4. And after that, the function is going to turn on. And what we can see here is that, let's just write that. If we say g of t equals sine t minus pi on 4 dot u t minus pi on 4. Well, we can say, well, this looks very, very similar to sine t with no shift. Because think about it. This part over here is just sine t. So we can make a generalization. First of all, we can say that we know that u of t minus c has the effect of suppressing the function for any value less than t. But when we have, say, sine of an argument times the Heaviside step function with the same argument, it's kind of equivalent to just the original function with a shift to the right. So we can say that sine of t minus pi on 4 dot ut minus pi on 4 is really identical to sine t shifted, kind of going to do that for a shift, shifted pi on 4 units to the right, because that's what this thing is over here. It's the original function shifted pi on 4 units to the right for t is greater than 0. And that's really important, because if you ever see a function that looks like this, like it's been shifted, we can immediately convert it to a function with a product of a Heaviside step in this form. And you'll see why that's important soon. So let's have a look at an example here. Let's say we have f of t equals e to the minus t. So we know what that's going to look like. It's going to look something like that. Yeah? 0, 1. And let's say we want to know what, I'll do it in a different color. Let's say f of t equals e to the minus t dot u t minus c. Oops, sorry, can't see that. So we know what ut minus c is going to look like. Ut minus c is going to look something like this. It's going to be, again, 0, 0, 0. And at some point, the value of c, this is going to take the value of 1. So if we identify c being, say, over here, we can say that e to the minus t, ut minus c, is going to be the product, again, of e to the minus t, which is this function over here, times by the pencil line, which is 0 for anything less than c, and 1 when beyond c. So the product of those two functions is going to be this. It's really going to be this thing here. That, and then it's going to come down like that. Now let's have a look at another question. So let's have a look at, say, f of t equals, say, u, t minus c, dot e to the minus t minus c. So immediately, I mean, for me, it looks quite scary. It's, whoa, what's going on here with everything? But do you remember what we said? That we said that if we had f of t equals sine, what was it again? Sine t minus c, u t minus c. That is identical to sine t, well, that's good, nice easy function, shifted c units along t-axis. And that looks very similar to a function t minus c, ut minus c. Ut minus c is the e to the minus t minus c is exactly the same form. So we can say that this is going to be very, very similar to e to the minus t. So I always draw at every stage. Okay. So we know that e to the minus t is going to look something like this. And if this form of ut minus c times times a function with the argument that's the same as the Heaviside step, in this case it is t minus c, we can say, well, that's the original function, exactly the same function, shifted c units along the t-axis for t is greater than 0. So that's going to be shifted over here. That's my red pen. And that's going to be c over there. Everything's going to be shifted. And it's only for t is greater than 0. So we can say that, well, for t is greater than 0, it begins over here, doesn't it, the original function? And that thing is shifted along. And then it's just going to be the rest of the function shifted along the same thing. So imagine that coming down, and it's going to look something like this. And that's going to go all the way to 0. It's going to tend to 0, at least anyway. So I hope that part was clear. And this is really important, because when we see something in this form, of u t minus c times a function with an argument that's the same as the argument of a Heaviside step function, we know what we're dealing with. It's just the same original function shifted c units along the t-axis only for t is greater than 0. The reason why it stops over here is because it only starts over here. For t is greater than 0, the original function starts here. And that's where the transform, or what the product of these two functions looks like. Shifted c units along the right axis only for t is greater than 0, and then everything else is the same. Okay, so now let's have a look at another function, a much easier one, in my opinion. When we have a function, we multiply it by ut minus 1 minus ut minus 2. So let's see what that's going to look like. So let's expand that. So we're going to have ut minus 1 e to the minus t minus ut minus 2 e to the minus t. Always put the Heaviside step function before the function, because it allows you to immediately see where the function is going to be starting from. So over here we can see ut minus 1, well, we know what that is. It's just going to be 0 for everything before t equals 1. And then it's going to turn on, it's going to be 1, it's going to take the value of 1 for all the values for t greater than 0. Greater than 1, sorry, t greater than 1. And if we multiply that by a function, we know that the function is going to be multiplied by 1 for every value for t greater than 1, and it's going to be 0 for every value less than t equals 1. In other words, it turns the function on, because the function times 1 is the function. I know that's obvious, but that's what it means by turning the function on. And then we've got minus ut minus 2, so this is telling me to subtract starting from t equals 2, the function of e to the minus t. So let's see, that we know that e to the t, f of t and t, is going to look something like that, 1 and 0. So ut minus 1, well, when t equals 1, let's say over here, we know the function is going to turn on. And ut minus 2, well, let's put, say, 2 over here. We're going to subtract this. So let's think about this in stages. So ut minus 1 e to the minus t is going to look like this, isn't it? It's going to be 0, 0, 0. When it gets to 1, whoop, it's going to turn on. And then it's going to go of e to the minus t all the way, all the way, all the way, all the way, as the original e to the minus t function looks like, yeah? Sorry, this is a little bit wonky, but hopefully you get the idea. So yes, you can see that it's going to look just like this, yeah? And what does ut minus 2 e to the minus t look like? Well, that's going to look like what's going to start at t equals 2. Before that, everything's going to be 0. I'm running out of different colors. So it's going to be 0, 0, 0, 0, 0, 0, 0 until we get to 2, and then the function's going to turn on. And then it's going to go like this again. So we now have got the pencil line, which is this function, ut minus 1 e to the minus t. And we've got the red line function, which is ut minus 2 e to the minus t. Okay? The e to the minus t is e to the minus t no matter what the Heaviside step function is. That the Heaviside step doesn't change the function at all. It just turns it on and off. So here we've got, well, on. So we're turning the function on here at t equals 1. We're turning the function on here at t equals 2. So can you see, if we subtract from the pencil line, the red line, what we're going to get? We've got basically this function, this big function here, starting at t equals 1, and we've got the red line function starting at t equals 2. Both at e to the minus t. They just start at different points. So if we subtract the red line from the pencil line, we're just going to be left with this part in the middle here, between 1 and 2. So in other words, we're going to be left with, I'll do this in a dotted line, it's going to be 0, 0, 0, because remember 0 minus 0 is 0. And then we're going to be left with this part over here. It's going to come down to over here. And then e to the minus t minus e to the minus t is 0. So then it's going to jump down to 0. So we're going to be left with this kind of dotted line. So if I was just to quickly kind of draw that again, we would end up with something that looks like that. And what this allows you to do in this form is really turn a function on and off, which is very powerful. So all you have to do if you want to turn the function on and off is multiply the function by u of t minus a, where the function turns on, and subtract it from ut minus b, where the function ends. And it's as simple as that. But it's a very powerful tool to be able to control when a function turns on and off. So in circuit analysis, for instance, you might have a voltage that turns on at a certain time and off at a later time, and you want to be able to represent that. So this is one of the ways that you can. Okay, so now let's have a look at what we think the Laplace transform of a Heaviside step function is. So it sounds a bit abstract. The Laplace function of a step function, well, it's actually really straightforward. So if we have a look, say, the Laplace, sorry, can't see that. The Laplace transform of u t minus c. If you're very smart, you probably know what it is already, but let's have a look. So the Laplace transform of u t minus c, remember, just try thinking about it a bit abstractly. Ut minus c is just turns on the function at c. So by definition of Laplace, that would be defined as the semi-infinite integral between positive infinity and 0 of the function, well in this case, whoops, sorry, you can't see that, of the function, which in this case is u, t minus c, times e to the minus st dt. So let's have a look at that, what that actually looks like. So we've got here the function, say f of t, and we've got t over here. And we know that e to the minus st is going to look something, all the way like that. Yeah, well, it doesn't actually touch 0, obviously, but never mind. It's going to be 0 and 1 over here. Now, if we, let's draw, sorry, that's not going to be 1, is it? That's going to be s. Yeah, that's going to take the value of s. Now, when, let's have the Heaviside step function being represented here. 0, and at some value it's going to turn on and it's going to be 1. Let's take the value of 1. Now, so if we take the product of e to the minus st and ut minus c, what we're going to end up with? Well, we're going to end up with, and remember, sorry, this is c, from c over here. We're going to end up with this part over here, aren't we? That part, and it's going to be 0 for everything else. So in other words, the integral, instead of going from infinity to 0, is just going to be e to the minus t, e to the minus st, which is the function, from positive infinity to c. Can you see that? No pun intended with the c. So again, normally we're going from positive infinity to 0, of e to the minus st times the function. Well, if we multiply e to the minus st by ut minus c, we end up with, again, ut minus c is the pencil line here. We're going to turn on the function when t equals c. For t is less than c, it's going to be 0. E to the minus t is 0. For greater than c, it's going to be e to the minus t. So we end up with this red line. Boom, boom, boom. So if we integrate that product, which is the red line, we can say that it's going to be equivalent to positive infinity, between positive infinity and c, because remember, less than c, it's going to be 0, of e to the minus st dt, which equals minus 1 on s, e to the minus st, evaluated between positive infinity and c. Yeah? Which equals, you can see that here, minus 1 on s, e to the minus infinity c, minus e to the minus sc. Yeah? So we know e to the minus infinity is going to be 0. As t tends to infinity, e to the minus whatever is going to be 0. And you minus 1 on s, 0 minus e to the minus sc. And therefore we can say that that's just simply going to be e to the minus sc on s. And that is the Laplace transform of u t minus c. Now let's consider a special case of ut minus c when c equals 0. What would the Laplace transform of that be, i.e. when c equals 0? So the Laplace transform of ut. So we know that already from what we've done, we know that the Laplace transform of u t minus c equals e to the minus cs on s. So we can immediately see here when c equals 0, e to the minus 0, 1, it's going to be 1 on s. We can see that algebraically. But I want to have a look at this from the graph. So I want to see this graphically. So if we see f of t over here, we've got t, and we know that e to the minus st is going to look something like that. Remember, we want to work out the Laplace transform of ut. That's going to be the semi-infinite, oh sorry, you can't see that. The semi-infinite integral between positive infinity and 0 of the function ut e to the minus st dt. So ut, well, we know what that is by now. Remember, e to the minus st, that's going to be s, that's going to be 0. So ut is going to be, and that's going to be 1. Yeah, remember, s doesn't have to be 1. So it's going to look like this. So we can say, therefore, that the product of e to the minus st and ut is going to be simply, it's just going to be e to the minus st, isn't it? For t is greater than 0. Can you see that? E to the minus st multiplied by 1 when t is greater than 0. For t is less than 0, it's going to be e to the minus st times 0. So it's actually going to look like that. Yep. And, well, we know very easily, we can see that this integral of infinity between infinity and 0 of the product of those two functions is just going to be the semi-infinite integral between positive infinity and 0 of e to the minus st dt, which equals minus 1 on s, e to the minus st, evaluated between infinity and 0, which equals minus 1 on s, e to the minus infinity, which is 0, minus e to the 0 is 1, equals 1 on s. And therefore, we can say the Laplace transform of u of t equals 1 on s, which is exactly the result that we would have got if we plugged in c equals 0 for the transform of ut minus c. It would have been e to the 0 on s, 1 on s. But now that we've seen that graphically as well. So we've seen two Laplace transforms. I know I'm doing this very, very tediously, very slowly, but I just want to make sure that I'm very clear on these points because all the understanding is going to pay off later. It's going to be required. So we've done two Laplace transforms, new ones. We've done the Laplace transform of ut and the Laplace transform of ut minus c. So we know that the Laplace transform of u of t equals 1 on s, and the Laplace transform of ut minus c equals e to the minus cs on s. So if the question was, what's the inverse Laplace transform of 1 on s, we know by implication that that's going to be u of t. So the inverse Laplace transform of 1 on s is ut, and the inverse Laplace transform of e to the minus cs on s is going to be ut minus c. And it's really important to keep writing these out quite a lot because they need to be very, very intuitive. But it poses a little bit of a problem because we've seen before that the inverse Laplace transform of 1 on s is a, because the Laplace transform of a is just a on s. Well, that's true, and this is also true. So if we have, let's say, the Laplace transform of, or let's say the inverse Laplace transform of a on s, that's just simply going to be a. We know it's going to be a. But now we can express it in terms of a Heaviside step function by saying a times ut. And it doesn't change the function at all, because remember that Laplace is defined in the definition between the limits of integration of positive infinity and 0. So we can now say, we can be a bit more sophisticated in our description of inverse Laplace transforms. Rather than just saying the inverse Laplace transform of a and s is just a, which it is, we can ask it's also a dot u of t as well. So just by way of example, if we had the inverse Laplace transform of 3 on s, we would say that would be equal to 3, but we can now say 3 ut. We had the inverse Laplace transform of 5 on s. I know this is silly, and not silly, but very simple, but I'm going to do it anyway. 5 on s, that's going to be equal to 5 u of t. If we had the inverse Laplace transform of e to the minus 3s on s, that's going to be equal to u, t minus c. In this case, c is 3, so it's going to be t minus 3. If we had the Laplace transform of e to the minus 5s on s, that's going to be equal to u, t minus 5, which is saying simply just that the function starts at t equals 5. And if you look at the definition of Laplace, you can see why the forward transform is going to be e to the minus 5s on s. And another thing we can say here is that if u of t really doesn't do anything to the definition of the Laplace transform, because it's effectively just turning the function on when t equals 0, or t is greater than 0. And since that is the definition of the Laplace forward transform, because the integral is between positive infinity and 0, we can say that the Laplace transform of, say, a constant, let's say a, is going to be the Laplace transform of a times ut, because it doesn't change it. And we can say that the Laplace transform of any function is exactly the same as saying the Laplace transform of the function times u of t, because we haven't changed anything. And you might ask, well, what's the point of that? Well, we'll get there. But let's consolidate that. So if we have the Laplace transform of 1, that's going to be equal to the Laplace transform of 1 dot u of t. If we have the Laplace transform of t, that's going to be exactly the same as the Laplace transform of t dot u of t. If we have the Laplace transform of f of t, that's going to be equal to the Laplace transform of f of t dot ut. And the point is that we can say this just by our understanding of the definition of u of t.